Okay. Hello. You should be able to see the desktop. And does everybody hear me? Is everything seem to be working? Camera on and all that? Yes. Okay. Still got people entering. Okay. Okay. So we're going to pick up where we left off the other day. Okay. Let's see. So first, uh, this is what you should read to get ready for the stuff we're going to do next about the GUI and how do you do interactive stuff. Okay, that'll be rendered too, but this is a nice introduction. This is an older Java book that they've made available for free, and there's this section 4.4, which is where they introduce the idea of Java's GUI system. Okay, and this is about 15 pages long, this section here. So read that section. It's a nice little introduction. Okay, and it goes up to, I think it's 15 pages. Yeah, see, it ends there. Okay, so that's their introduction. Then they have a whole chapter that's more in detail. So they do an introductory overview, and then they do a more detailed go run through of it. Okay, so read the introduction first, and then you can start reading this. This chapter is more closer to 50 pages. It's a whole chapter, and we want the idea here is that it's really good for you to learn a graphical user interface system. If you've never used any kind of GUI code, the Java one's not a bad one to learn. Nobody uses it anymore, but it is a really well designed one. It is a really good one. Uh, now for GUIs, people are a lot more likely to use .NET, Windows, Apple's native libraries, or the HTML and JavaScript. So Java kind of got pushed aside, between writing native Windows programs, writing native Apple programs, and writing web apps. That's what the world does right now. And then there's also cell phone apps, which are they're a bit of a mixture of all of those. But Java GUIs didn't fit into any of those. Yeah. The closest is the Android phone. The Android phone still is a Java GUI, but it's not this one. It's a different library. It's Java, but it's not this particular GUI library. It's not the one built into Java. I think Android, has pretty much its own GUI library built on top of their operating system. Okay, so the Java GUI library is a really good one. It's just that Java didn't end up with a role to play in the way we use computers these days. Except where it works, the role Java has, it maybe you know, is on servers. It's just hugely used on servers. So it's doing all the database accessing, and all the code that's running on the servers is almost all. It's pretty much supplanted C++ for that kind of use. Okay, but it didn't. Its GUI use died about 10 years ago. It just kind of ended. I think the only program you might be using right now that it's actually a Java GUI is Eclipse. Yeah, Eclipse is a famous example of a very elaborate program written as a pure Java GUI. And there's the things like Dr. Java, and there's little programs like that floating around that are Java GUIs. Okay, but it's a good library to learn. Okay, it's if you learn the Java GUI library, it's a pretty good basis for understanding what we mean by GUI libraries in general. Okay, but all the documentation for it is old. Nobody's writing books on Java GUI anymore, so you have to look for stuff that's 10 or more years old. That's about like what this is. This was originally written in 2005. Then it was updated recently. The people who wrote it updated, but it was originally written for 2005. So it's mostly about what things were like 15 years ago. Okay. And at the time, they were real hopeful that Java GUIs would become the main GUI. What JavaScript is now is what they hoped Java would be. The people who invented Java thought that Java would be where JavaScript is right now, and it turned out it didn't work out that way. Okay, so we'll start with talking about GUIs, and we'll use that as a way to make our renderer interactive. So you can use mouse and keyboard, and you can interact with it like a game would. You can interact with the renderer. Okay, so that's about the best reading for this I've been able to find that's free. Okay, now next thing, does anybody have any question about the homework assignment? The homework assignment, it's due what? It's due Tuesday. Okay, it's due in a little less than a week. Does anybody have any general question about it? Anything that's funny? Anybody anything that notice anything funny, or have a general question about the homework assignment? Okay. As usual, if you have specific questions about your code, attach your code in an email, send me an email, ask questions. Okay. Oh, and like I mentioned the other day, this thing's out of date already. That's just, but all you gotta do to fix that is change 29 to 30, and it works. Okay, they've upgraded from, and it'll be 31 in a few weeks. Yeah, if you come back to this in another week or two, it won't be 30 anymore. It'll be 31. Then after you download it, you got to make sure you also change this script file that runs ImageMagick. You have to edit it and change that 29 to a 30 also. Okay, so you got to do both those changes. You download version 30 and then update the script to 30. And if you've got the 29 version on your computer, you don't need to update it. Who knows what little minor change they made. These releases are really minor because they go through them like every week or two. There's a new release. They release their software really often. So you wouldn't want to bother with upgrading this software to the most recent version. Okay, so but if you haven't downloaded it yet and you're just downloading it, you'll need to change that number up there to 30, and then change that number to 30, and then change that number to 30. Make those two changes, and it should be fine. Okay. All right.
Professor,
Mm-hmm.
when I do these changes, I'm still getting an error saying invalid parameter for 30.
I didn't get that error message. I think make sure that you put this folder in the right place. Okay.
Okay.
Make sure you put this folder. Let me try something. See, there's a convert command in Windows somewhere. See, when I typed convert, I got an answer back. There's a convert command in Windows somewhere. I don't know where it is.
Yes, Professor, I tried that, but I don't know how to pass delay to that convert command.
Well, you have to make sure that you have this thing in the right place. You have to have it on your C drive.
Yeah.
And if you're getting that delay not valid, that's almost always because you're using the wrong convert command. You're using this one that's built into Windows. And I'm not even sure. I think it's a command for converting virtual machines or something like that. I'm not sure. But see, we're using the convert command that's in this folder here. So we push that folder into the path and then call convert, which will then have this path at the front of the have this folder at the front of the path. So it'll run this version of convert. But that error message is coming from this program, this other convert. I know that because it's happened before. It's this other convert that's giving you the error message.
I downloaded ImageMagick and installed it in my Windows system, Professor, and then I'm using convert.
Well, we can look into, we can, like with screen sharing, could probably figure out what's going on, because Yeah, I know where the error message is coming from. It's coming from the other convert command. So the question is, why isn't this convert command in your path? Because if this line of code is right,
Mm-hmm.
then the path is set to that. We have this at the front of the path, and then you're using that convert, not the other convert. So we'll have to look through it. We're using screen sharing. There's probably some simple little mistake somewhere, okay? Because yeah, that's why this thing needs to be there, And I don't think people should install ImageMagick, because then you've got their convert fighting with this built-in convert of Windows, and that stuff gets to be a real nightmare when you have two programs on your computer with the same, like this convert might be needed by some Windows program. Okay,
Okay.
so this built-in convert is part of Windows, and it might be needed. I don't know if I can find out what convert it is. Oh yeah, convert FAT to NTFS. See, it's what I thought. It doesn't convert virtual machines. It converts file systems. It's for converting from a FAT to an NTFS file system. All right, so it's built into Windows. So that convert command is part of the Windows operating system. So it's not a good idea to clobber it. It's not a good idea to clobber it by putting somebody else's convert in front of it in the path. So that's one reason why I avoid a lot of times using installers, because you can end up with really strange problems when you use installers if they have names in them, that they install names that are part of the names that the operating system uses, like convert is part of Windows. There's a convert. Mm-hmm, mm-hmm. Yeah. So this should work, but with screen sharing, they'll probably figure out what's going wrong with your machine. What little problem there might be, we'll probably figure it out by looking in detail. Okay. So okay. So any other question about the homework assignment? Anything else about the homework? Okay. Um, let's go. Remember, what we're doing is we're tracing through the render with one program. Okay, and we'll see. We're using this triangle program. That was the one we started with. Okay. Okay. So, now we know about the scene. We know about model. We know about adding a model to the scene. We know about adding vertices. We know about constructing vertices, adding the vertices to the model, constructing line segments, adding line segments to the model. So now the model's all built. So the whole scene is built. So that little bit of code creates a scene holding one triangle, three vertices, three edges, and together they make up one triangle. Okay. Then we create a frame buffer to hold the output. Okay. And then what we want to start talking about, what we've been talking about, is this step here. Render the scene into the frame buffer. Fill the pixels of the frame buffer with what would represent that scene, as if we were taking a picture with a camera. Okay, and the scene has a camera in it. It's centered at the origin, staring down the negative z-axis, and we can either use a perspective camera or an orthographic camera. By default, we're using a perspective camera, like our eye is, or like a real camera is. Okay, so what happens here? So we call the render static method in the pipeline class. Okay, and the pipeline class was imported from the pipeline package. Okay, so let me open up the render. There's the pipeline package, and there's the pipeline class. And there's the render method in the static. There's the static method that renders. Notice it returns void. This is typical kind of graphics programming. It's not very functional. The render has the side effect of mutating the viewport. Okay, it doesn't return what it computes. It mutates one of its parameters, and that's what functional programmers will tell you is the source of all evil. But that's the way we write these days. We still write most of our code that way. The render takes in a scene data structure. That's its real input. That's its output. Remember, if we go back and look at our picture, the whole point of the way we think of it is the render produces this as an output, and it takes this as an input. So it's like a function. And if we were doing this in a functional programming language, the renderer would be a function that took this as input and returned that as a return type. But since we're using a Java language and we're doing things in a more traditional way, the renderer takes in the scene, but it also takes in the frame buffer, which it mutates, and it returns nothing. Okay, so that's just, yeah, that's a common way of doing things. Okay, all right. So we're now notice that final here and final here mean that you can't. What they really mean is this scene, the thing. It doesn't mean you can't update the scene. It means that the actual object that this reference variable points at can't be changed, but what's inside that object can be changed. So this reference variable has to point at one specific object. You can't change what it points at, but what's inside that object can change. Same here. This says that this reference variable points at a specific viewport, and you cannot change what viewport it points at, but you can sure stick pixels into that viewport. So you can mutate the viewport. So this is telling you that you're not going to ever work with any other view, that this thing's going to always point to the same viewport all the time. It's never going to change what viewport it points at. And this is going to point to the same scene all the time. Okay? And then what we want to do is for every model in the scene, we want to render the model. The scene is a bunch of models. A scene is a list of models. We render one model at a time. So we go to that model and draw its pixels in the frame buffer. Then we go to that model and draw its pixels in the frame buffer. Then we go to that model and draw its pixels in the frame buffer. So we look at here and we see that for each model in the scene, we check if the model's visible, because that's a neat little trick. If we go and look at the model class, the model class has a Boolean visible, so you can just toggle that and make things disappear, which it's real good for debugging, and it's real good. It just makes things easier to work with. Instead of having to remove a model from a scene if you want it to disappear, you can just mark it as visible as false, and the model, you can make a model just disappear from the scene. And that's a lot easier than removing the model from the list and re-entering the model for the list if you want to make it appear again. Okay, so most renderers have this little trick that you can mark a model as visible. So if the model is visible, we render it. If it's not visible, well, this renderer produces a lot of error logging messages. It logs a lot of things. So if the model is not visible, you shouldn't do anything, but I do log a message that there was a hidden model. That's useful for debugging. In a debugging scenario, you might want to know that model that didn't appear on the screen because you thought it should have, didn't appear because you had marked it as hidden. So maybe you should go figure out why you marked it as hidden. So it's useful in a debugging sense to say things like, oh, there's a hidden model in the scene. Okay. Now, the log message method, you go down here to log, it checks if debugging is turned on. Okay, so if pipeline debugging is turned on, or if model debugging is turned on. Now, if you go back over here, the model has another variable, a Boolean called debug. You could either debug the whole scene, or you can debug one model in the scene. If you want to debug the whole scene, you turn on pipeline debugging. If you want to debug only one model, you turn on debugging in that model. Okay, so this is kind of a nice, this is what I mean by like what you need to do when you start writing sophisticated uh, software systems. Sophisticated software systems, one of the things they need is logging. You need to have a way for them to produce messages to let you know what's going on. And it's not just for debugging. Logging is usually used in production to find out if there's problems with the system. So in a production system, at runtime, you can turn on logging to see if there's some kind of, you find out what might be going wrong in a server or in a system. So software needs logging. Software needs a way of saying, I just did something, log some information. I just did something, log some information. I did something, log some information. And then there should be a way of turning it off and turning it on. In this case, I have a debug variable for this static method. So if this is true, then everything is logged. On the other hand, if this is false, then you have the option of turning debugging on in one model. You can tell a model to be debugged, okay? And in the pipeline package, the logging functions check both those variables. So log message, log vertex, log line segment, they all check, is the global debugging turned on or is this model debugging turned on? Okay, so up here, if the model's visible, we log a message that we're about to render that model. If the model's invisible, we log a message that there was a hidden model. And notice this is where the model name can be useful. See, I'll say hidden model, and then I use the name in the model. See, that was the other field in the model. So now you see how these fields are used. They're really useful for debugging. This can make the model visible or invisible. This turns off or on debugging. And in your logging messages, you use this name. Makes it a lot easier when you read the log output to figure out where that stuff came from. You can see, you give your models nice names when you instantiate them. And then when you're looking at the log output, you can see which model is which. You can see the log output from different models. Okay, so I use the model name in the log messages. Okay, all right. See, so the model name is passed into every log message. Okay, okay. Or I pass the model. Like here I'm logging some information and I just give it the model so I can get the name out of the model. Here I'm logging a string. So I'm just logging a string here. And I put the model, I interpolated the model name into the middle of that string. Actually, I passed the model here. So, but otherwise I would have to have passed two strings, you know. Okay, so okay, so now the next thing the render does is it does a little sanity check of the model. Okay, especially when you're doing your homework assignments, it's real easy to goof up. I do this all the time. You build a model, and then if you build a model like we did here, it's real easy to forget, like to add a line segment. I've done it. I put all the vertices in the model and forget to add line segments to the model. So the line segment list is empty. Or the other way around. I might just somehow not have put enough vertices. Like what if I have a model with 10 line segments and 2 vertices? It's probably not right. Okay, so this sanity check is an attempt at the render to give you a heads up when something's wrong. So you look at the check, and it says if the vertex list is empty, print an error message, a warning. See, you get warnings from this method. If there's no vertices, that's a warning. If there's no line segments, that's a warning. Okay? Okay. So right now it's just later on I'll add more things to this this little sanity check. Right now it's just making sure that you have some vertices and that you have some line segments. Okay. So that actually helps catch little errors. Otherwise, the render if you don't do this, well, what will happen is if you have an empty vertex list or an empty line segment list, it doesn't stop the render. You just get these warnings, but then you'll get real strange error messages from from the renderer. So hopefully seeing these warnings will give you an idea of why you're getting strange error messages from the renderer. Because the renderer kind of just blows up if it gets an empty line segment list or it gets an empty vertex list. Okay, but the error, whenever programs blow up, the error messages when they blow up can be kind of mystical. So this is to try to give you a sense of why something may have blown up. Okay, so that's got nothing to do with the render. Like no GPU is going to do that for you. You know, OpenGL doesn't do these kind of things for you. But since this is our own render, I can go ahead and put that in there and just say, if there's something wrong with this model, go ahead and print out a warning message. Okay, so that just checks that everything, you know, just gives you a quick warning if you did something really goofy like forget vertices or forget line segments. Okay, so then now print out what the model looks like. Okay, well, the vertices. Okay, log the vertices of this model. Okay, now if the logging's turned off, this doesn't do anything. But if the logging's turned on, it lets you see what the vertices look like at the beginning. Before you do anything in the render, it lets you see what the vertices look like. So it prints out a list of the vertices. Okay, Then it does the first step, project. So project the vertices into the image plane. Yeah, and if we go look at our pictures of rendering, you know, we have these little pictures that kind of, the projection is when all the vertices out here go over to here. Okay, or in this picture, you're projecting all the vertices. That's the first step. Project the vertices into the image plane. He called it the canvas in this picture. We're going to call it the image plane. So you notice he calls it here image. The image is sitting inside here. So call this, I think a better name for this is the image plane. Okay. So project. Now notice that the projection is only done on vertices. You don't project line segments. The code over here is projecting, well, the way the function's written, it projects the model using that camera. Because why does it need to know the camera? Because it needs to know if it's doing an orthographic or a perspective projection. So, okay, so this could be a parallel projection or a perspective projection. So this method needs to be told what the seeing camera is saying. So this method takes the camera and the model. And what it does, it projects, you can't tell that from here, it projects the vertices, and it doesn't touch the line segments. So when we look inside the code, we'll see that it projects the vertices and doesn't touch the line segments. But here I wrote it in a more functional style. Notice it returns a new model. What it does is it takes this model in, and it gives you out that model there as a model. So it builds this model that's living in the image plane. So it takes a original model in and it does not mutate it. See, and this is where I'm just starting to use a little bit more modern kind of a style of programming. It doesn't mutate that model. It builds a new model that's living in this plane here. Okay, then this is a static method in the projection file. So you go over here to in the same package, there's the projection file. Notice that putting a static method in a file, I could have just as easily put all the static methods in this one file. I could have just had everything in this one file, but that would make it harder to see. It's kind of nice to look and see that what you see is a pipeline of a projection and a rasterization. It's really kind of artificial. All of that could have been in one file because I'm just using static methods in there, static methods in there, and static methods in there. I chose to put them in separate files because it just makes it look better. You get a better. It makes it easier to document it in Java docs. Instead of trying to document one huge file, you're documenting 3 smaller files. And also you see it in the structure that there is 3 things. A pipeline made up of projection rasterization. Later on, the renderer will have a pipeline in about a dozen stages. Eventually, we'll get to where there's about a dozen of these stages. All the stages could be wrapped into one file because everything's going to be static methods, but that's really a bad way to do things. So it's just a packaging thing. It's just a way of presenting it. I put the projection in its own file and rasterization in its own file. Okay, so you open up projection and there's a little bit of documentation and then a pretty short method. What it's going to do, it takes in a model and a camera. It's going to project the vertices. So it creates a new vertex list to hold the projected vertices. It checks, and then for every vertex in the vertex list, so it iterates through this vertex list. For every vertex it finds in there, it puts a new vertex in that vertex list. The projected vertex gets, you take a vertex from there, you create a new projected vertex and put it in there. Okay, so for every vertex in the model, well, is the camera perspective or else, parallel? So there's 2 different formulas. If it's a perspective camera, this is the calculation. And if it's an orthographic camera, this is the calculation of the projected vertex. And we did that calculation, remember, is just that formula there. See? That formula there is that formula there. Yeah. So that formula there is that formula there, and there it is in code. And you remember, yeah, they have the minus sign in the denominator. I even put I put the minus. I wrote it here the same way it's written over here. Okay, the the projected x, the projected x is the camera x divided by the negative of the camera z variable, and over here this coordinate is in the camera space because the camera's over here, and we're projecting. He didn't put the little c's out here, x sub c, y sub z, z sub c, to represent x, y, and z in camera coordinates. Some people put a little e as a subscript there, x sub e for I coordinate system. So see, he calls it the view plane. Unfortunately, this can be called the view plane, the camera plane, the I plane. Everybody's got their own name for these things. Okay, so I've tried to consistently call this the camera coordinate system. Later on, we'll have a different coordinate system that we'll call the view coordinate system. Okay, so we'll use the view plane for a different idea. So right now, this is the camera plane. Okay, so you're going to project the camera coordinates to the projected point. And he calls them x prime, y prime. Over here, they're x sub p, y sub p for projected. Okay, all right. So simple little formula. Remember, similar triangles. That triangle is similar to that triangle. So the ratio of that edge to that edge is the same as the ratio of that edge to that edge. And those are the four edges they're using in this formula here. They're not using the hypotenuse. They're not using the Pythagorean theorem. They're not using the hypotenuse. They're using a similar triangle using this leg and that leg. Okay, so the x prime, and notice that the x prime is that leg, x is that leg, d is that leg, and negative z is, see, that leg there. So they're comparing the two legs. They're using the ratio of the two legs. Okay, and similar, and that gives them. Then you solve for x prime, which is the point we're interested in. You solve for x prime, and you just get that simple little formula. Okay, pretty easy. And then that's render. That's what your GPU. You pay a lot of money for it to do that one little calculation. Except it does a lot more than that one little calculation. But this is what makes it a 3D renderer. This projection transformation is really, it's what smashes things from, if you think about it, it's really the heart of it, because it's what smashes things from it's what smashes things from 3D space to 2D space. That's what a render really, really, really does. So projection is the single most important step. You need to smash everything from 3D into 2D. Everything else the renderer does is icing on the cake, giving you nice effects, doing proper lighting, doing all kinds of shading. Everything after that is just kind of nice, but the heart of the render is shoving everything from three-dimensional space somehow into two-dimensional space. Okay. All right. Then the harder part is, okay, now the next step is once you've got that vertex there and that vertex there, you need to turn on the pixels that connect it. That's where the line segments come in. Okay. So this line segment doesn't really matter at all. We don't really do anything with it. But when we project that vertex to there and that vertex to there, then we want to say, oh, there's a line segment between those two vertices, but between this vertex and this vertex, we want to fill in the pixels. So that's the rasterization step. So we go back to the pipeline. Okay, so we've just done the projection stage. The model has got new, notice that we're now working with model 2. We were rendering this model. We've replaced that model with this model. We didn't mutate this model. We replaced it with this model. It's got new vertices in it, so we log the new model. Okay. Here we logged the original model. Notice that I logged it as being in camera coordinates. Then the new model's logged as being in projected coordinates. So before we do anything, the model's sitting here in camera space. So 0 means we haven't done anything yet. So we're essentially step 0, where the model's in camera coordinates, project. The new model is in projected coordinates, so we log it. Okay, if we have logging turned on. If we don't have logging turned on, we don't see this information. Okay, now we need to rasterize. Okay, now what we're going to do is switch to the put a for loop here, and we're going to just say for every line segment in this model. So if you go back to this picture here, where is it? Remember, we rendered every model in this list. So we're rendering this model. Okay, we projected all the vertices. Now we're going to rasterize the line segments. So we drop down to here and we say, okay, for every line segment, rasterize this line segment, rasterize this line segment. Okay, so to render a scene is a list of models. The broad outline is render that model, then render that model, then render that model. Okay, when you will render a model, the steps are project the vertices. So that's done all in one step. Project all the vertices, then go over here and say, okay, now render that line segment, render that line segment, render that line segment. Okay, so now you go through a loop of rendering the line, of rasterizing. In this case, what we mean is rasterize the line segments. Okay, so now we have a loop for every line segment in the new model. Now, the line segments in this model are the same as the line segments we were in the original model. If we go over to projection, we see that when we return the new model, we use the new vertex list with the old line segment list. Okay. Now, there's something important there. We have to be very careful about something. If this is vertex 0 and this is vertex 1, there's a line segment that goes from vertex 0 to vertex 1. When we project this vertex down to here, we better make sure that the projected vertex 0 in that list is the projected vertex 0 in this list, and that the projection of vertex 1 is the vertex 1 in this list, because we're not changing the line segments. If the projected vertices appeared in the list in a different order here, then the line segments would be meaningless, because the line segments index by order in the vertex list. So the line segment for this would be 0, 1, from vertex 0 to vertex 1. So since you don't change the line segment list, you better have these vertices in the right order. And that, of course, that's what this thing does. It iterates through this vertex list in the order it is and puts new vertices in the new list in the same order. So every new vertex is put into this list in the same order as the vertex is replacing. But it's important to realize that that has to be done very carefully. You have to make sure that when you replace these vertices with new vertices, you keep them in the same order. So this vertex is replaced by another vertex in a different list. But if this is the first vertex in this list, it better be the first vertex in this list. If this one's the fifth one in this list, its projection better be the fifth one in the new list. Okay, so we're recycling the line segment list. Okay, so then we go over here and in the pipeline. So for every line segment in the new model, okay, that's really the same line segment list from the old model, but it's a new vertex list. First, we log the line segment just to let you see what we're about to rasterize. So if logging is turned off, you don't see this, but we're about to. It says here we're about to rasterize a line segment. Okay, then you call the function that rasterizes. Now here you say rasterize this line segment into the frame buffer. So here's the first place the frame buffer is shown up. We're now about to put something in the frame buffer. Projection didn't put anything in the frame buffer. Projection took a model and built a new model. It didn't put anything in the frame buffer yet. Rasterization put something in the frame buffer. So it says, put this line segment into the viewport. And it also says, and here's where you're going to find the vertices for that line segment. So this line segment has 2 indices in it, and this thing holds now I could have passed the vertex list here. I mean, because this line segment needs to look things up in the vertex list, and I could have either passed the vertex list here or passed the model. I just thought it was easier to pass the model. Okay, but it actually didn't really need to pass the whole model at this point. What this guy really needs is just the vertex list from that model. Okay, So now what's the rasterize method look like? So that's the rasterize method in this function. So that's the last stage. And this is the hard part, okay? This is where things get kind of tricky. The rasterization stage is way harder than projection, okay? Now, uh, in this picture here, this is what we've projected into. This is the camera's view rectangle, okay? So that's this rectangle here. That's the rectangle you've projected everything into. Now here they show it as a rectangle. In our case, it's a square, and it was sitting in the z equals -1 axis. Though it really doesn't matter. Notice I don't even tell you what z coordinate is here. As far as I'm concerned, this is just a two-dimensional square, and it goes from -1 to 1 on the x-axis and from -1 to 1 on the y-axis. It happens to be at z equals -1, but it doesn't really matter so much here. Everything has been projected into line segments in this plane. Now, they may not actually be sitting inside this rectangle. We could have a line segment that sticks out. Just, here in this picture, no object sticks out of that view volume, but an object could be sticking out of that view volume, and then it needs to be clipped because you're only supposed to see what's inside that rectangle. So if that sphere starts sliding to the right, as it slides to the right, it hits that edge, then it should start getting cut off. I mean, the sphere will stick out of the view volume, but in the picture, the sphere should get cut, okay? And, if we run one of our renders, just show you, you know, if you go off the edge, things should be clipped off. Now, in this render, I can actually turn off and on clipping. So if I turn off the clipping, what went off that edge for some reason appears over here. We're not clear. It's not clear why that would be. It shouldn't happen. So clipping should be on. So things that now this model is really there. You can see it's still really there. See, the idea is I want you to know that it's really still there. In this other picture, when that sphere drifts off to that side, the sphere doesn't itself get chopped, only its image gets chopped. The sphere is still intact. It's just maybe partially sticking outside of this volume. So it's the render that's going to have to figure out to not draw the part of the sphere that's sticking out of that box. Okay, and our render lets you actually turn off and on clipping. And if you turn off clipping, in this case, it actually causes things to appear over here. On the other hand, that's not the same as for the top and bottom edges. Now clipping is turned off, I'll turn it back on, and I'll go up to the top. I'll go to the top edge. Okay, if I go off the top edge, this thing's still there, but if I turn clipping off, it doesn't fold down to here. The renderer crashes actually, because that's causing a buffer overflow on the array. Okay, that's causing a bad pixel. It's causing the frame buffer to be overrun. So we're gonna have to see, like, why is the top edge and the bottom edge is the same. You don't the left edge. If you go off the left edge, you reappear in the right edge. You go off the right edge, you reappear in the left edge. If you go off the top edge, you crash the render. If you go off the bottom edge, you also crash the render. So we'll eventually see why that would be the case. But the render should clip. The idea is there should be clipping. When these guys move up or go off this way or go off that way, they should get clipped in this plane here. But the objects don't get nothing in the render will clip that sphere. The sphere will stay a sphere. When the sphere floats over here, it's still a sphere. It's in the rendering that it gets chopped, that part of the sphere gets chopped off. Okay, so that's going to be important that we do the chopping when we render, we don't go back and somehow cut up that model. Okay, so we've got line segments in this plane, We would like them to be inside this rectangle, but in fact, we don't have control over them. They might actually be, just like we saw, somebody might move their model off the screen. So as the model's moving off the screen, it's partly in here and partly out of this rectangle. We need to figure out what pixels to paint over here. This is the frame buffer. So we have a line segment in here somewhere, and we need to figure out what pixels to turn off and on over here to represent that line segment. And that's a pretty tricky thing to do. And so we introduce an intermediate idea, something that called the logical pixels and the logical pixel plane. Okay, so this is called the pixel plane. I give it some. I call it the pixel plane or the logical viewport. Remember, this is actually not quite the frame buffer. This is a viewport in the frame buffer. The frame buffer might actually be quite a bit larger, but we render into a region of the viewport. So this is actually the view. So a lot of times I say frame buffer over here, but it's really the viewport in the frame buffer. So the frame buffer may actually be a lot bigger. This may just be a sub-region. It might be the whole frame buffer, but it may also just be a little part of the frame buffer. And then this would be viewport coordinates. This is the upper left-hand corner of the viewport. So that's not necessarily the upper left-hand corner of the frame buffer itself. But we render into a viewport. We don't really render into the whole frame buffer. Okay, so I need to figure out what pixels to turn on here to represent a line that's over here. And I create this intermediate space. The motivation for this comes from the following. You could take this thing here. You can do one of two things. You could take this viewport and scrunch it to fit inside of here. And essentially, that pixel there would be a little pixel up there. And that pixel there would be a little pixel next to it. So you could take this thing and scrunch it into there, and then you could see where the line was, and you could say, oh, that's what pixels I need to turn on over here. So you can imagine that if you had a line over here, you'd translate it over to here by saying, well, let's take the frame buffer, scrunch it down into here, and then when we look at the line, we'll see what pixels it overlaps. Okay, that would be one idea. Another idea is you could say, well, I don't want to scrunch the frame buffer. I'll take this picture and stretch it so that it stretches across this frame buffer. So I would take this corner and put it over to here, stretch this corner over to here, stretch this corner down to here, and I'd stretch this thing over the frame buffer, and then I get the same idea. My line would now travel across this frame buffer, and I could say, oh, that pixel, that pixel, that pixel, that pixel. Okay, now that's not a bad idea, but the trouble is it's harder than you think to decide what pixels to paint in this frame buffer. If you take your line, now let me show you, there's some pictures that show you this. It's not so obvious when you have a line going through here. Like if you take this thing here and stretch it out to here, just because you have a line through there, it's not obvious what pixels to turn on. Okay, so here's another picture to look at. I can't remember where. No, I hope I have the. Yeah, here. When you go from that when you go from that point to that point, see the little squares? Those are the pixels. Like, should you turn on that square? Like, well, this one's not such, is there, I'm sort of looking for one that, like, only like here. See when the line goes from there to there? Should you turn on, there's a little bit of, see, it covers a little corner of that and a little corner of this. Which one should be turned on? Is that corner of this one? Notice that you have to turn on this whole square or you have to turn on this whole square. Should you turn on that square or both? Notice that the line only chops off a tiny little piece of that square and a little tiny piece of that one. Notice it goes through the heart of that one. So, that's not a hard decision. The line goes right through the middle of that square, so turn it on. Now, this one, there's still a fair, it cuts off, it kind of almost in the middle of that square. Okay, but this one's a good example that it's not clear. Should you turn on both those or should you turn on the one above or the one below? It actually is not simple. If you just see a line, if you just had a line going through here, that would not make it easy to figure out what pixels to turn on and what pixels not to turn on. Okay, all right. See if I have another picture like that. Like this blue line. Okay, is it obvious which pixels you would turn on? Let's see. Okay, it starts in this pixel. It's in the corner of the pixel. Should you turn it on or not? Let's suppose you do. Then it kind of goes through the middle of that pixel. Okay. Now, what about here? Should you turn on that pixel, or both? What's the right thing to do? So you kind of chop off that, you lop off, you're in the upper left-hand corner of this pixel. You're kind of almost through the middle. You might make the case that you're more in this one, but should you ignore this one? You know, and then as you go up, like what about this pixel here? You chop off a little corner of it. Should you turn it on or not? Or should you just turn on the one above it? You probably definitely want to turn the one on above it because you go through a lot of it. Should you turn on this one or not? Okay. It's not so clear how you'd want to do these. Now, let me show you another thing that's kind of fun. Here's a website where they have no, I'm sorry, not that one. This one. Somebody created a little interactive website that's really like, here they show you there's a vertical line, there's a 45-degree line, there's a line that's neither vertical nor 45-degree, and then notice it goes up two pixels over, up 2 pixels over. Then they have they give you a little thing where you could draw pixels, and they tell you to start doing it yourself. Like they say, okay, connect that to there. Okay, how would you? Okay, so you go, I'll just go like this, and you're gonna not, that would be really dumb, right? Okay, so there's a real dumb way to get from one to the other. So then you start. It's actually kind of clever. If you try to do this, you find that it's not so obvious how you should get, like, what if you go up and over 2, up and over 2, up and over 2, up and over 2? Oh, that's not a good idea either. So now you think, okay, maybe I should go up and over 3. Okay, so maybe I would go up and over 3, maybe up and over 3, up and over 3, up and over 3, and it turns out, oh, that worked pretty well. Okay, but that's, if you just drew the line from there, I wish they'd actually add that thing where you draw the line from there to there. The line doesn't really help a lot. In this case, it would be up and over 3, up 1 over 3, up 1 over 3 is a pretty good way. And one thing, we usually never do that. We don't put 2 pixels in a column. You might say that that looks good to you, but most renderers won't do it that way. Okay, so they will put only 1 pixel per column. Okay, so they would do it that way. So there's only 1 pixel per, so they wouldn't put one there. Now, notice that doesn't necessarily look bad at all. Okay, compare that to this. It's not so clear. Again, it's not obvious what's the right way to turn on pixels. Okay, so to give us an algorithm, we introduce this guy down here. This guy is something that sits between here and here to help us figure out which pixels we should turn on here. So we're going to still, now what we're going to do is, the idea we like is, if you got a line in there, take this thing and stretch it over this thing, and then watch where the line goes. That's actually the right idea. Take this guy and stretch him over that. The stretching of this rectangle over this rectangle is a linear function, and we'll write the formulas for that linear function. So that linear function will literally just say, what it does in math is what you would do here is just saying, take this guy, stretch him over this. Then look at the line segment. Except what we'll do is we'll stretch this guy over this guy. And this guy doesn't need to be stretched over this guy. What this guy here is there's a dot for the center of every one of these pixels. Every pixel here is represented by a dot here, which represents the center of a pixel. So there's a little square around each one of these dots. Okay, we're going to take this, stretch it over this. Our line will now pass between these dots, just like this picture here. This picture here is this one here, but it's actually these two combined. It's the dots, which we call logical pixels, and it's the squares, the actual pixels that are represented. So what we're going to do is, if we decide that that's the dot we want to use, we color in that whole pixel. If we're going to use that dot, we color in that whole pixel. The dots live over here, the pixels live over here. The dots live in this logical view plane, the pixels live in the viewport. But we actually think of this thing is stretched over this thing, and this thing is laid on top of this thing. Now let me show you another picture that is a super clever way of showing this. See, this one says making Webgl dance. This is a slideshow. I'm just gonna go through it real quick. He's trying to show ideas of rasterization, and he's got this brilliant picture here. Okay, now he's not doing line segments, he's doing triangles. Okay, here is this picture here, but in an animation, you know, dots representing logical pixels, squares representing pixels, and then you've got he's got a moving triangle. Okay, and yeah, over here, it's this guy and this guy. The geometry from here has been stretched to sit on top of this. So in this picture here, and in this animation here, the geometry from, I wish I had two monitors here. This is, the geometry from here has been stretched over the pixel plane. The geometry has been stretched over the pixel plane. The geometry has been stretched over the pixel plane. So this has been stretched over to here. Okay, and here's how he shows you real nicely what's really going on. See, there really is two things. There really is, well, here he's showing the map from here to here. See, this is the pixel plane. Here's the frame buffer or the viewport. See, pixel plane, viewport. Okay. Over here, you have, I wish you could stop this animation. I really wish you could just stop it. We're interested in this edge. We're trying to figure out what pixels to paint for that edge. He's interested in the whole triangle. And what he's doing is, if any dot is inside the triangle, he makes it red, and then it gets projected over. You see, here's one that never changes. Any dot that's inside the edges of the triangle is red, and it's projected over to here and turned on. Okay. Any dot that, now see, watch that dot. See how it turned red, and now it's going to turn black because it's outside. Now it's back inside, now it's outside. If you went over to here, you'd see that pixel there. It's on, now it's off. Now that pixel's on again, now it's off again. But he only showed the projection for one pixel. This is he called it vector world. I don't know where he got that name. This is the pixel plane. Okay, the logical pixels. The term that most people seem to use over here is logical pixels. He calls this raster world. Well, a better word for that is the frame buffer, or the viewport in the frame buffer. Okay, he called it vector world, raster world. Okay. Okay. So, but that picture shows you how, that's what we want to do. We want to stretch the geometry over the logical pixel plane, then use the logical pixels to figure out which things over here. He's got an easier job here. He only has to figure out, is the dot inside the red triangle or not. We have actually a harder job. It's actually a little trickier to do line. Notice he's not doing the edge. He's doing the whole triangle. We need to do three line segments. We're not painting the inside of the triangle. We're painting the three lines that are the edges, which is actually a different problem. So here he's actually doing a slightly easier problem. It's easier to rasterize a triangle than it is to rasterize a line. A little bit easier. Okay. But this really demonstrates the idea pretty well. Okay. Then he squashes them back over, and then he does some other stuff. And let me advance through here. There's another picture later on. I think the order of this stuff is goofy. It's not in a logical order. here is the idea we're talking about. Camera looking at some object. This is the projection plane here that he's going to project. See, notice he's already essentially put the pixels in it. So the camera is going to project this object, and he put the projection plane behind the object, which it doesn't really matter where the projection plane is. If you look at our pictures of projection, it's actually kind of a does it really matter if you project forward to that plane or backward to that plane? Turns out, no, it doesn't. We almost always, in our brains, every book in the world shows it as projecting forward to that plane, but it turns out mathematically, and when you write the code, it doesn't make a bit of difference if you project forward or backwards. You can do either one. Doesn't matter where you put that projection plane, you'll get the same answer. So you can think of the projection plane as in the middle here. You can think of everything as being squashed to the middle. So you can either project forward or you can project backward. It doesn't matter mathematically. So here he's actually drawn a picture where he's projecting back to this plane here. And in that plane, he's drawn the pixel, which is also in our, we have that same picture here. See, we project here. This shows the pixels already in that projection plane. So in a sense, this shows that projection plane with the pixels already in them, ready to hold the data. Okay, now so he shows it now. See, now he's got it. Well, he's ready to project there. See, now you're supposed to imagine now it's been projected into the frame buffer. No, it's been projected into the view rectangle, and there's the frame buffer pixels superimposed. Now in this slide, he doesn't show the logical pixels. Logical pixels are at the center of each of those pixels. Okay, so he's just showing something else here. Then he goes back to that picture again. Okay, so but your people are trying to get across the same idea over and over again in different ways. We got a camera, we got objects, we got a plane, and we're projecting. The camera sees the objects and they get projected to the plane the way the camera sees them. Then the hard part is which of these pixels in this plane, which of those pixels which pixels do you turn on? Later on, what color do you turn them on? Which pixels turn on and which pixels get left background color. Okay, so he's got some nice animations here. The best one is did I skip it? No, yeah, I skipped it. This one. This is the one that really, I think this is the one that really brings together what in this, this is a static image, but there's three things there, and they're here. The geometry from here is this triangle. You stretch it over the logical pixel plane, that's these dots. Then once you're in this logical plane, you use the dots. The key is you use the dots as a way to figure out which pixels to turn on. And you see that here. You use the dots. Is the dot in the triangle or is the dot? Well, that never left the triangle. Yeah. Like, is the dot in the triangle or is the dot outside the triangle? Okay. Is the dot outside or inside? Use the dots to figure out. Notice that you don't use the squares, you use the dots. Okay. Now let me show you another thing. Everybody says a pixel is a little square. So you always hear people say that these things are pixels. There's a famous paper. This guy worked for he's one of the persons who helped invent computer graphics. He worked for Microsoft, he worked for Pixar, he worked for Industrial Light and Magic, he worked for all these people. Notice the name of the paper. A pixel's not a little square, a pixel's not a little square, a pixel's not a little square. He kept wanting, he wanted people not to think about little squares. What he wants them to think about is these dots. When people do graphics, The point of this paper is, if you think of these squares, you get messed up. You should think of these dots. These dots are the pixels. Technically, they're called sample points. So the right word for these is sample point. But so actually, if you want to, you could call these sample points and call these pixels. Otherwise, you can call this a logical pixel and this a physical pixel. Logical pixel, physical pixel. But the one that's really important is this pixel, the logical pixel. And then here he wants people to actually call that the pixel. He wants the pixel to be, he wants the pixel to be the little dot. Okay. He wants the little dot. We'll get that picture back up. He wants the little dots to be the pixels. Okay. And so he titled his paper emphatically, a pixel is not a little square, a pixel is not a little square. And this was written a long time ago. This was written back in 1995. Okay. And it was trying to get people who do graphics programming to think of these little dots. Each little dot has a region of interest. Each little dot is responsible for a region of the screen. And one of his emphasis is it doesn't have to be a square. Your dot could be responsible for overlapping circles. Okay. So for example, that dot is influenced by some of the same area as that dot because they have overlapping influence. See, in this way, this dot is only influenced by what's inside here, and this dot is only influenced by what's inside here. These dots don't have any overlap. And he's pointing out that that's actually not the right way to think. Eventually you want to think of what's the region of influence that this dot has, and that dot could have overlapping regions of influence. That's called anti-aliasing, and that gives you better pictures. So this picture, if you think of little squares, and then you think of, well, this little square, I figure out what its color is, and this little square, I figure out what this color is, that leads to not good design. You're better off thinking, what's that dot? What's that dot influenced by? And then that dot gets a color depending on what it's influenced by, and then you paint that square, that color. But first you'd say, what's the dot? What's its region of influence? Then decide the color of the dot, then you decide the color of the square that the dot is sitting in. Okay. So he keeps emphasizing that idea that you have the pixels, the dot. Okay. And in signal processing, it's called a sample point. I don't remember if he uses the word sample point in here. So every once in a while, he uses the word sample a few places. Each point sample. Okay. Point samples are essentially his pixels are what in a branch of what's called image processing or signal processing. Those are called the point sample. Oh, yeah, actually, here it is. A pixel is a point sample. So what is a pixel? So where is he? This is page 2. Yeah, a pixel is a point sample. Okay. So is it a square? His point of view, no, a pixel is not a square. It should be that sample point there. Okay. All right. Now, how do we now use this? Okay. A line here is this rectangle stretched over this pixel frame, this logical pixel plane. So this gets stretched over here. So I got a line segment stretching through it like this. Notice that the vertices don't have to land on these pixels by any means. So that vertex just landed somewhere in this plane. And that vertex landed somewhere in this plane. And that vertex landed somewhere else in this plane. They didn't land on, the likelihood they land on one of these dots is pretty small. They usually land, they land in between dots. These vertices are the projected vertices. That's a projected vertex, a projected vertex, a projected vertex, a project. So they're vertices in here. But we've taken this guy and stretched him over this guy. And now we've got these vertices in this plane. Now let's look at the code, and we'll see that we can actually follow from here to here. If we look at the rasterization code, we're done with the projection code, done with the model code. Here's the rasterize. Oh yeah, the code's down below. Actually, I want this picture, the picture is over here too. So I want to jump back and forth between the code and the picture. So the code is here. Now here I wrote it as this thing is stretched over this thing, which is, so I drew it as a sequence. Over here I drew it as this guy, this guy. I mean, the geometry starts here, the pixels end up here, but we need this guy in between. So we kind of go from here to here to here. And here I drew it as you go from here to here to here. Okay, so how do you get from here to here? Let's look in the code to go from here to here. That's the idea of I'm going to stretch this thing over this. That's done right there. Four equations. You need to take the you need to take the x coordinate and the y coordinate of one endpoint and send it from. You take one endpoint, take its x and y coordinate, send it from here to here, and then you do it with the other point. Its x and y coordinate gets sent from up here to down here. Okay, so this is the formula. It's a simple, it's just a little mx. It actually just is mx plus b written in a funny way. There's the b, there's the slope. Well, actually no, it's mx plus b written in a kind of a funny, yeah, because there's the well, it's written as it's actually written in the point slope equation of the line. It's written in the you're used to that, but there's also the point slope equation of a line. Okay, and then there's there's those two equations of a line. If you go back to calculus, you actually use this one in calculus. That's the equation of a tangent line. You almost never use this one in calculus. This is the one you're taught in high school. Then you get to calculus and we tell you, don't use that. Use this one instead, because that's the slope, the derivative, and that's the point that you're taking the derivative of at. Okay, so that's the point slope. That's what I'm using here. Point slope. Okay, so I did a calculation and found the point slope equation of a line. And whenever you do stretching, you're doing linear equations. If I tell you to stretch one rectangle over another rectangle, so I'm stretching this rectangle over this rectangle, I'm using linear equations. Okay, so there's the point slope equation of the line that stretches. That's the horizontal stretching equation, and this is the vertical stretching equation. If you go back to this picture, -1 to 1 needs to be stretched from here to here. That's the horizontal stretching. And then from -1 to 1 vertically has to be stretched from here to here. So you think of them as independent stretching. You have to do a certain amount of stretching horizontally and a certain amount of stretching vertically. The amount of stretch is the slope. The slope of the line is what tells you how much the line is being stretched by. It, you probably never thought of it that way, but the derivative is a stretch factor. If I do something real simple, like a real quick graph, oh, where's lines? Lines. Here's an x-axis, here's a y-axis. Okay, and then here's a line. There's just there's some line. Okay, now here's what we mean by a line. A slope is a stretching factor. Okay, take an interval over here, put a little tick mark there and a tick mark there. Okay, now that goes up and over to a tick mark here. That goes up and over to a tick mark here. I didn't draw very well. Okay. And what happens is that interval got stretched to that interval by going up, over, up, over. What I really did is I stretched this to this. If this line has slope larger than 1, I've actually made it get bigger. If this line has slope less than 1, this got compressed. Okay. And if this line is 45 degrees, this thing will be the same as this thing. It's actually real common in engineering and physics to think of these lines as stretching factors, that this interval here is being stretched to an interval over here, or this interval over here is being compressed to an interval over here. And the amount of stretching is the slope, okay? And that's what we're using over here. That's what we're doing in these equations over here, okay? We've got this point now living in the pixel plane. Now we do a step. We round that point to its nearest neighbor. We actually don't rasterize the line that we're given. We cheat and we move it over to here. And this one will be moved over to here. And this one will be moved over to here. And this one will be moved over to here. Okay, so that's in the code. That's the next step in the code. Snap each vertex to its nearest neighbor. We ran out of time. Does anybody see a problem with that? Look at the picture, and you should see a really big problem, which is actually a real big problem in graphics. It causes grief. Does anybody see something wrong? Which line is above which other line? Okay. Is the blue line above the black line? But if you snap this one to here, because that's who he's closest to. See, he's not close to there. He's closer to here. You know, his distance from here is closer. And he rounds to there. But this guy's close to that one. When you snap him to there and you snap him to there, then this blue line will rasterize like that, and the black line will rasterize the row above it. So what's the problem? You can go ahead. I don't care if you talk to me. If you might as well, you can say things. The lines get switched. Logically, the black line is below the blue line. But then when you render it, the black line will be above the blue line. That's clearly, those are called artifacts. When things go wrong like that, they're called artifacts. And there's another picture that shows the same kind of, not that one. Oh, this one shows another example of that kind of problem. If this blue line is moving to the right, this blue line, this is an animation. The blue line is traveling to the right. At first, the blue line would rasterize on top of the red line. But then at some point, the blue line, this pixel would move over to here, and the blue line would start rasterizing diagonally. The bottom end would snap over to here, but the top end would stay over here. See, the line's got a little bit of a slope to it. So what happens is the blue line looks vertical. Then it looks slightly sloped to the right. Then it snaps back to the vertical. Then it snaps slightly to the right. Then it snaps back to vertical. And what you get, if this was an animation, is a jagged line that keeps jittering. And this happens in real animations. You get jittering lines, where instead of the line smoothly moving to the right, because of the way we round pixels, see, right now it's going to rasterize as the red line, and then it's going to rasterize again as the red line, but then it slides over a tiny bit and it rasterizes that red line sloping. But they should have shown it one more time. If you do the next step over, it would rasterize as a red line going straight up. So it's straight up, slope, straight up, slope. So that's jittering. Okay, so this rounding trick is a problem. This step is problematic. but we keep it there. And a really sophisticated renderer, and this is where they put a lot of effort into, is to solve this problem. We're not writing a sophisticated render, we're writing a simple render, so we're not going to solve this problem. But honestly, that's one of the hard parts of a real render, is solving this little problem of these pixels jumping around, and this problem of what happens when lines swap their order. Okay, so we're almost through the code. We'll finish it on Tuesday. We've got one more idea left to do. What we now have are the two endpoints of the line segment snapped to the logical pixels. So that guy snapped to there, this guy snapped to there. And now we have the last step, find the pixels in between. The last step is to paint the pixels in between. After you snap the vertices to the grid, sometimes people call it snapping it to the grid. You snap the endpoint to the grid, snap that endpoint to the grid, then paint the pixels in between. So that'd be the last bit of code to do in here. And actually, that's where most of the code. It's what's left is a simple idea. Actually, what's left is a simpler idea. These transformations here are the harder idea. What's left is the simpler idea, and so we can do that real quick on Tuesday, and then we'll be done with the rasterizing. Okay. All right. So, anybody have any question? Because we went over. Anybody have any question? Okay. If you have a question about the homework, send me an email or arrange a meeting, and we can talk about anything with the homework too. So I'll go ahead and stop sharing now, and I'll go ahead and end the meeting, and see you on Tuesday. Have a nice weekend. Bye.